Good morning, I'm Junbin from Beihang University. I will present our work, MultiLanes, providing virtualized storage for stable virtualization on many cores. Our work mainly focuses on the server consolidation scenario that plans multiple workloads on a single node of data centers for high utilization. As the many-core architecture exhibits more and more powerful computing capacity, the server consolidation becomes an even more important method to fully utilize the hardware resource. As we know, virtualization is a prevailing approach for server consolidation. Such examples include Zhang, KVM, VMware, OpenVZ, vServer, and Linux container. There are two main virtualization approaches, parallel virtualization and OS level virtualization. First, we make a comparison of them. The parallel virtualization exhibits more poor error performance because we can see from the graph. Each error request from VM applications needs to go through the deep error stack, which consists of several redundant layers, such as VFS and file system. In contrast, OS level virtualization exhibits near native performance because of the sharing of the kernel service. However, in OS level virtualization, different error requests from different containers go through the shared error stack. The sharing of data structures and nodes within the error stack can lead to scalability issues on many cores. The interference is usually masked by the slow hardware performance. However, the advent of non-volatile memories exhibits the scalability issues because the device built with them deliver high performance in terms of bandwidth and latency, which shifts the bottleneck from hardware to software. In order to motivate our work, we create a simple macro benchmark which performs the buffer write to a 256 MB file inside each container and varies the number of containers from 1 to 16. The experiment is performed on a 16-core machine and with use a round disk to evaluate the fastest device. We evaluate these three popular OS level virtualization approaches, including OpenVZ, vServer, and Linux container. The evaluation shows the average throughput of containers dramatically decreases with the increased number of containers on ext3. The evaluation on ext4 and BTRFS presents the similar results. It is noteworthy that XFS scales well and the workload owing to its optimization. In particular, it delays block allocation and associated metadata journey until the dirty pages are to be flashed to the disk. However, XFS also exhibits poor scalability and other workloads, which will be described later. The macro benchmark demonstrates that scalability bottleneck becomes a dominant factor in performance of virtualized environment on fast devices. We also make a detailed breakdown of the contention with the shared error stack. The table shows the knock statistics when running 16 containers collected during the macro benchmark. We can see from the table. And the 16 containers, there are millions of knock bounds among 16 cores. Accordingly, the total wait time for acquiring knocks can reach as much as 100 seconds. We note that the benchmark can complete within 4 seconds and one single container. So there are two factors that cause severe contention in our stack. First, global critical sections limit scaling on many cores. For example, the journey block device layer of X3 protects several buffer lists and internal buffer states with corresponding nodes. Second, frequent remote cache accesses will hamper system performance. In order to address the issues, we proposed MultiLanes to eliminate the interference by avoiding the data sharing within our stack between different containers. This graph shows the overview of our approach, MultiLanes. The name means isolated our path. We eliminate the contention between containers by providing an isolated stack for each container. Traditionally, the L stack in Linux consists of the VFS file system. In order to eliminate the contention with the VFS layer, we partition the data structures and nodes within the VFS, providing a private VFS abstraction for each container. Then, we realize a virtualized block device driver to run a guest file system for each container to avoid the data contention with the file system layer. In order to run a guest file system, we map an image file on the host file system as a virtualized storage device for each container, which provides isolation, flexibility, and manageability. This graph shows the mapping between logic blocks of an image file of a container and the physical blocks on the host. The block mapping is created and maintained by the host file system. So one intuitive approach to completing our request from guest file system is to leverage the host file system to read and write data on the host device. However, this intuitive approach comes with two issues. First, it deepens the IO path, as each IO request needs to go through the guest and host file system. So how to retain IO efficiency of OS-level virtualization? Second, the host file system itself scales poorly on many cores, as the intuitive approach needs the environment of the host file system to complete data transmission between buffer and the device. The poor scalability of a host file system will decrease the overall performance. To address the first problem, we propose our request remapping mechanism. The technique delivers our request from guest file system to the host driver directly. As we know, most file system devise a mapping routine for block mapping. We export the API from the host file system. It first gets the block mapping by invoking the mapping interface of the host file system. In Linux, each our request from the graph we can see in Linux each our request consists of several segments which are contiguous on the device but are not necessarily contiguous in the buffer. The virtualized driver should first remap the segment of each R request with the help of the mapping interface. We can see after remapping, the contiguous logical blocks are not necessarily contiguous on the host, as the host file system does not always allocate blocks contiguous for a file. Hence, each orange R request may be remapped to several R requests of the host file system. In particular, after remapping, we combine the segments which are contiguous on the host device as a whole and allocate a R request of the host device for them, and then we create a new R request for each of the remaining segments. And last, the R request will be delivered to the host driver without the environment of the host file system. So this is a virtualized driver model. After receiving a R request from the guest file system, the virtualized driver first remaps the R request. Virtualized driver will look up the logical block number in the block mapping cache. If it is hit, virtualized driver directly gets the physical number of it. Otherwise, the virtualized driver will invoke the mapping interface exported by the host file system and then stores the block mapping entry into the table. As the mapping process of the host file system usually calls file system joining, concurrent block mapping cache misses will cause severe contention on the host. Our approach is to decouple the blocking mapping process. Decouple the blocking mapping process from block request handling. In particular, we employ a translation thread pool for block mapping, then constrain all the translation threads to a small set of cores, and at the same time adopt a prefetch mechanism to reduce communication cost. Now, we introduce the second key component, PVFS, Partitioned Virtual File System. As we know, virtual file system in Linux provides a generic file system interface for applications to access underlying file systems in a uniform way. The use of global data structures and protecting nodes in VFS will harm the OS scalability. The table shows the shared data structures and nodes with the VFS. Compared to iteratively eliminate or mitigate scalability bottlenecks in VFS, we adopt a straightforward approach that completely partitions the data structures and nodes within VFS, thus completely eliminating contention with the VFS layer and as well as improving data locality of VFS data structures. Here we perform experiments to evaluate the performance and scalability of MultiLanes against the Linux container as the baseline on a 16-core Intel machine. As when we conduct the evaluation, we have not a high-performance SSD at hand. We use the RAM disk to emulate PCM SSD is appropriate, as MultiLanes does not concern about the specific storage media, as long as the storage is fast enough. We use Linux container as the baseline. We perform a set of macro benchmarks and a set of macro benchmarks. The macro benchmarks consist of metadata-intensive work nodes and data-intensive work node. The macro benchmark consists of FileBench, VML, and FileBench file server, and MyCircle. The first macro benchmark is a metadata-intensive work node, which consists of create, rename, and delete operations. We write this macro benchmark in order to enumerate the contribution of each MultiLanes component, as the metadata-intensive work node can stress both the VFS layer and the underlying file system layer. The experiment is carried on for 3 situations: the baseline, MultiLanes without PVFS, and complete MultiLanes. The result on EX3, in the graph shows the throughput on Linux decrease dramatically with the increased number of containers. And in contrast, the MultiLanes without PVFS exhibits much better scalability than the baseline and achieves the improvement over the baseline when the number of containers exceeds 2. The performance gain mainly comes from the file system isolation while virtualized storage devices. Complete MultiLanes further improved the performance. Owing to the partitioned virtual file system, which eliminates the contention within the VFS layer and exhibits nearly null scalability. We note that, single one container, the throughput of complete MultiLanes even outperforms the MultiLanes without the PVFS and the baseline. This is because of the use of the private VFS data structures. In particular, there are much less directory entries in the directory cache than original VFS. We also performed the experiment on the other 3 file systems and get the similar results. We use the L zone to evaluate MultiLanes and data-intensive workloads against the baseline, including sequential buffer rise, sequential direct rise, and random buffer rise. This graph shows the result of sequential buffer rise on EX3. We can see that the average throughput of the baseline scales poorly with the number of containers. In contrast, MultiLanes exhibits nearly null scalability and outperforms the baseline beyond 2 containers. We also evaluate MultiLanes on the other 3 file systems, EX4, XFS, and BTFS. For EX4 and BTFS, we got the similar results, but as XFS scales well and the buffer rise, our approach exhibits almost the equivalent performance against it. Here we present the result of sequential direct rise. We can see that the average throughput of the baseline decreases dramatically with the increased number of containers. In contrast, MultiLanes exhibits nearly null scalability and outperforms the baseline when the number of containers exceeds 2. For the other 3 file systems, we also got the similar results. For the random buffer rise, the results are similar to sequential buffer rise. Now, we use application-level benchmark file bench VML to evaluate MultiLanes against the baseline. We can see that with the increased number of containers, the throughput of baseline significantly decreases. In contrast, MultiLanes exhibits nearly null scalability with the number of containers and outperforms the baseline. We also can see that MultiLanes outperforms the baseline even at 1 single container. This is also because of the use of private VFS data structures. As the VML workload consists of many metadata operations. We also evaluate MultiLanes on the other 3 file systems and got the similar results. For the file bench file server workload, we also can see that the baseline scales poorly with the number of containers. MultiLanes exhibit marginally performance degradation. We note that at 1 container there are some overheads for MultiLanes. However, it outperforms the baseline when the number of containers exceeds 2. We also evaluate MultiLanes on the other 3 file systems and got the similar results. Here, we present the result of MultiLanes and the RTP workload compared to the baseline. We also can see that the baseline scales poorly with the number of containers. In contrast, MultiLanes exhibits nearly null scalability and outperforms the baseline when the number of containers exceeds 2. For EX4 and BTFS, we got the similar results. XFS again scales well and this workload. Now, what about the overhead of MultiLanes? We use extensive of benchmarks to further evaluate the potential overhead of MultiLanes, which consists of Apache build, file bench web server, and file bench stream write. Apache build is a less file-intensive workload. File bench web server is a read-intensive workload. Stream write is a write-intensive workload. We run each benchmark program inside a single container to highlight the overhead of MultiLanes. This is the result of Apache build workload. We can see that MultiLanes exhibits almost equivalent performance against the baseline. For the web server workload, MultiLanes exhibits almost equivalent performance against the baseline also. But for the stream write, up to 44% overhead is observed due to the frequent block mapping catch misses. Now we make a conclusion. The interference within the shared L stack among containers could adversely affect the performance on many cores. An isolated L stack for each container is built to eliminate contention. The isolated L stack consists of the virtualized storage device and the partitioned virtual file system. The virtual storage device is tuned to be efficient and scalable. We adopt a synchronous bypass strategy to avoid most of the virtualization overhead and constrain all the translation thread to a small set of cores and employing a prefetch mechanism to reduce communication cost. Thank you.
All right, Kai Shen from University of Rochester. Interesting work. One thing I wonder is whether you end up with adding a large memory footprint because of those separate channels that have been created. So is it the increase in the memory footprint of your system?
In memory operations, you
mean? When you have all the separate lanes, you know, those replicated I/O stack, I tend to think that it would tend to occupy larger memory space. And would that be the case? Or is that going to be a problem in your judgment?
You mean the operations in the memory will cause contention?
Not contention, just simply when you have those multiple lanes of those I/O stack, you would have more stuff in memory, right? Is that the case?
Yes.
Would that be a issue in terms of memory space usage?
No. Our approach is complementary to previous approaches. Previous approaches mainly focus on the hardware resources such as CPU and memory schedule to minimize the interference between containers. But our work mainly focuses on the scalability issues existing in the L stack to eliminate contention on many cores.
All right.
Okay, this is Yang from the University of California, Santa Cruz. So this is great work. And actually, my question is more like, so we observe that for XFS, when there are a large number of containers, the performance of XFS is much better than that of ext4. So my question is like more to the developer Ted So of ext4. So do we still have like a big lock in ext4 that prevents ext4 to scale better?
You mean XFS scales well on many cores?
Yeah, XFL, from your benchmark, it scales much better than ext4. So my question is more like to Ted So. So I'm wondering whether ext4 still has a big lock somewhere in the kernel so to prevent it scales better to support multi-tenants.
Yeah, I was going to take this offline. There are all sorts of questions about which version of the kernel he was using.
Yeah,
there are a lot of VFS scalability that has been fixed in newer versions of the kernel, but I don't know that we want to necessarily try to dive into that right now.
We can take this offline. Thanks. Thank you. Great work.
Yeah, I have another question that's relevant to this work. That is, so you started with looking at this so-called OS level virtualization. But the way you're doing right now is to have those separate channels. It looks more and more like a full machine virtualization where you virtualize the whole machine with all the I/O stack in it. So do you see this sort of shift toward the actual full machine virtualization and whether there's any, I guess, thought about contrasting with that?
we don't evaluate MultiLanes against the full virtualization approach. But we can see from the previous papers that OS level virtualization exhibits outperforms that much better than the full virtualization approaches.
All right, thank you.